Now we're going to talk about intermolecular forces. Intermolecular forces are forces that are between molecules. So what these do is they connect one molecule to another molecule. Technically, we're only supposed to use these terms for molecular covalence, but we expanded a little bit to talk about those that also work with network covalence and ionic compounds and metallic bonds. So in our minds, we are viewing this as what takes the small pieces and joins them together into something we can actually see. And so when I say see, I mean literally see. So for example, this is a crystal of copper sulfate, and it's far more than just one copper and one sulfate joined together. It's a whole bunch of them joined together into something that we can physically see. So usually we're going to be talking about a solid or a liquid, frequently a crystal form. The only time we can see gas is if it happens to be a colored gas, and that's usually an indication that it's also a poisonous gas. So most of the gases that we see, like nitrogen that's in our atmosphere, we don't so much notice. So I'm going to list the types that I'm going to go over. And I'm deliberately listing them in this order, though it's not necessarily the order I'm going to go over them. So we have our network covalence. And our network covalence, we have already said, have strong covalent bonds. Then we have our ionics. And we're going to be talking about electrostatic attractions. Then we're going to talk about hydrogen bonds, what's called dipole-dipole forces, dispersion forces, which are also called London dispersion forces, which is frequently abbreviated LDFs. You see that in some notations, or it's abbreviated dispersion force. And then we're going to talk about metallic bonds. I gave you an overview of these types in the last lesson. We're going to talk about them in a little bit more detail this time. These three are all the kinds that we'll see when we have a molecular covalent compound. Molecular covalent can be any of those three. These two together, you will sometimes hear called in a group of things called van der Waals forces. Depending on the teacher and the text, you might hear them more often than others. But if you hear van der Waals forces, it's these type of forces. But in network or molecular covalence, we can see all three of these types. Now we'll talk about them in a little bit more detail. As we mentioned last time, network covalent includes things like diamonds. As a result, it is a very, very, very strong attraction from one thing to another. You learned last time that there are two cases that we want you to know for this class, carbon and SiO2, in the diamond and in the quartz form, respectively. When we talk about ionic bonds, this is also described as an electrostatic attraction between oppositely charged ions. And a very common example that we use is NaCl. The example I have in front of me of this blue rock, which isn't really a rock, it's a salt crystal, is copper sulfate. With these ionic bonds, the strength of the ionic bond depends on two things. The two things that the strength depends on are the charge of the ions and the distance between the ions. Okay, so when I say charge of ions, what I mean is, for example, if I was comparing NaCl to MgS, for example, you know from the position on the periodic table what sodium's charge is. Sodium's in group 1, so it's going to have a charge of +1. Chlorine has a charge of -1. Magnesium has a charge of +2. Sulfur has a charge of -2. So if you want to imagine which ones do you think stick together better, the one with kind of like bigger magnets. The one with higher charges sticks better. And the consequence of that is when we say it sticks better, is it's going to have a stronger force, stronger attractive force between them, which is going to correlate with some other properties like a higher melting point or a higher boiling point. So if you want to look at the ions, you're looking at how big the number is, mostly the absolute value. So if I gave you a different example of like AlCl3, aluminum is a +1, aluminum is a +3, and chlorine is a -1. I would expect aluminum chloride also to stick together better than sodium chloride. Comparing it to magnesium sulfide is going to be a little bit harder. The next thing we look at is the distance between the ions. I could elaborate on this by saying smaller ions can get closer together, which is going to give us a stronger attractive force. And a stronger attractive force will also correlate with like a higher melting point or something like that. It's the same as the analogy we use with how electrons are held by a nucleus. The closer they are to the nucleus, the more strongly they're held. So here we would be looking at ionic radius. So suppose I was going to ask you to compare NAF and NABR. The first thing I would look at is charge. Always look at charge first. +1, -1, +1, -1. No difference there. Now, if this is sodium, this might be fluoride. Na+. Bromine is going to be quite a bit bigger than fluoride because it has 2 more shells of electrons. One of the reasons we did periodic trends before this is to help understand this. So if I were looking at the distance between them, I'm comparing that distance versus that distance. With the smaller ions can get closer together, which is going to give us a stronger force. Now we have some problems where we want you to decide which one has the stronger ionic bond.